Welcome, everyone, to today's webinar hosted by the Institute of Navigation titled Low-Cost Inertial Aiding for Deep Urban Tightly Coupled Multi-Antenna Precise GNSS. Written by James E. Yoder and Todd E. Humphreys, a navigation paper published in the spring 2023 issue of Navigation, the Journal of the Institute of Navigation. Today's webinar is being presented by Professor Todd Humphreys, one of the paper's authors. Professor Humphreys holds the Ashley H. Priddy Centennial Professorship in Engineering in the Department of Aerospace Engineering and Engineering Mechanics at the University of Texas at Austin. He is director of the Wireless Networking and Communications Group and of the UT Radio Navigation Laboratory, where he specializes in the application of optimal detection and estimation techniques to positioning, navigation, and timing. His awards include the UT Regents Outstanding Teaching Award, the National Science Foundation's Career Award, and the Presidential Early Career Award for Scientists and Engineers, also by the National Science Foundation, as well as our favorite, the ION Thurlow Award. He is a fellow of the Institute of Navigation and of the Royal Institute of Navigation. The full technical paper, along with many others, is available from the Navigation Open Access website at navi, that's navi.ion.org, where you can read, download, cite, and share this and other valuable research content. You'll have the opportunity to ask questions. Please use the Q&A box in your viewer. Today's webinar is being recorded and will be available from our website and social media channels later this week. Now we will turn the time over to Professor Humphreys. Thank you for being here.
Thank you, Rick. It's a pleasure to be here, and I thank the Institute of Navigation for giving me this opportunity. I'm coming at you live from the great state of Texas, where we'll be talking about low-cost inertial aiding for deep urban tightly coupled multi-antenna precise GNSS. James Yoder, my former graduate student, led this work, and I want to give him the lion's share of the credit today. I wish he had been able to join me, but he is currently employed by SpaceX. He's on the GNC team for Starship. And if you know anything about what's going on with Starship this week, you can understand that he's somewhat busy. The outline of the paper will go as I like to read papers. I don't tend to go through a paper linearly, just from the introduction all the way to the end. I mostly read the introduction, and then I jump right away to the results. And if the results interest me enough, then I'll go back and get into the technical material to determine, what made it tick. So we'll go from the results to looking under the hood at our algorithm, and then we've got some bonus material at the end. So first, motivation. We can pose a question to begin the motivation. Question being, how reliable must self-driving cars be? Now, a human level reliability is about 100 million miles between system-caused fatality. So humans are actually quite good drivers. Elon Musk has said in the past that he would like 2 times human reliability as his target before introducing, say, full self-driving in the widest possible sense. Ford in 2019 said, no, it needs to be 100x. And Intel and Mobileye back in 2017 said something more like 1,000x. We believe that it's somewhere between the 2x and 100x reliability. We don't think the lower side, the 2x side, will work long term, because think about this. At only 2x human reliability, and with a modest fleet of, say, 1 million vehicles, one would expect a vehicle-caused fatality every 5 days. And we just don't believe that any manufacturer could withstand the ensuing product liability lawsuits and reputational damage that would happen, that would cause every 5 days. We're already seeing some of this with Tesla's, the lawsuits against Tesla and the investigations by the Department of Transportation. So to achieve such high overall reliability, something that would really be well beyond human reliability, the risk allocation to each subsystem will be extremely tight. And the focus of the talk today is on the precise high-integrity GNSS-based positioning, navigation, and timing that might underpin the vehicle's sense of its location and orientation. So this is one of the vehicle subsystems, and we believe that whatever problem might arise because of this subsystem needs to be strictly curtailed in its risk. Now, many of you are aware that there are a couple of different variants of GNSS-based positioning. There is standard pseudo-range-based positioning. There is precise positioning that is based off of the carrier phase measurement. The precise positioning historically has been something that worked well out in open fields, out in large mining pits, but not typically in urban environments. And poor experiences with GNSS in early self-driving development gave it a bad reputation. This is a screenshot from 2016 South by Southwest Interactive, where Google was presenting some of their self-driving car efforts. And Chris Urmson at the time pointed out that the white square to the left of the vehicle was the position as determined by GNSS, whereas the vehicle itself is in its true location with respect to the side of the road. And he pointed out that GNSS just wouldn't cut it. This kind of mentality seeped into many different self-driving efforts where people's sense of its precision was, say, improperly influenced by some of the earlier GNSS capabilities. I believe that this is an inaccurate sense of what is the full capability of GNSS, and I hope that I can persuade you of that by the time the presentation is over. But just to give you a sense for how self-driving has eschewed GNSS, has avoided it, this is a recent video taken by one of these YouTube testers that likes to get the very most recent FSD, full self-driving beta software installed, and then kick the tires by testing it, in this case, in San Francisco. What you'll notice is that this test driver tries to make a right-hand turn under full self-driving. And this is, like I say, a really recent variant. I'm not straw-manning this by picking some older variant. This is from February. And as he makes a right-hand turn, the car gets confused between interpretation of the lane and interpretation of some railway tracks that are on the right-hand side of the road, and ends up turning to the right. You can see this proceed as the right-hand turn is executed. This is under full self-driving as the Tesla is trying to navigate using camera images mostly alone. So here it gets confused and ends up following the railroad tracks. The driver has to pull it around. The fact that this is still a problem in 2023 is appalling to me. And it shows that people inside Tesla just don't have a sense for the additional benefits that GNSS could offer them, and could offer them with very low cost. This kind of error would never be a problem even if you were using very, very simple maps, but if you had precise GNSS. So a thesis statement for the presentation today is that precise positioning is becoming more robust even as its price falls. And I believe that as with MEMS-based inertial sensing, precise positioning should be viewed as a floor requirement, that no semi or highly automated vehicle should lack it. It ought to be on every Tesla. It ought to be on every Waymo vehicle, and it should be using some of the latest variants of precise positioning, such as what we'll be presenting today. Here's the historical problem. The reason why people fell out of love with GNSS is because, as I said before, they had some early bad experiences. And it is true that precise positioning doesn't work in the severe multipath and signal blockage common in urban environments. It historically has not worked well in these environments. And these are environments in which these self-driving vehicles are meant to operate. So that historical problem has to be addressed. In fact, it is sometimes the case that when you fix the integers to the wrong value, or you have a convergence problem, that precise positioning can yield worse performance than the standard solution in the face of this urban multipath and signal blockage. So that's the problem we face today. What we wanted to do was to combine precise positioning with MEMS inertial sensing and a vehicle model, and test this in deep urban environments so that we could get all weather positioning in that environment. And our research goal is to explore the accuracy and integrity limits of precise carrier phase-based GNSS in the urban environment. So this is the paper that we finally published, as mentioned at the top of the hour, published in on March 7th. That's James's smiling face. And we encourage you to read the paper. I'm only going to give a kind of top-level overview of it today, but it has a lot of good material in the paper, and it cites some of our earlier work. Also, I won't have time today to go over all of the other good work being done around the world, at Wuhan University, for example, and other places that are pursuing low-cost, precise positioning for self-driving vehicles also. But I do believe that our work represents the state of the art. No other published work has demonstrated such performance as we have shown in the urban environment. And we also have a public data set with which anyone who believes they could challenge these results and do better are welcome to give it a try on the public data set. Let's talk a bit about the benchmark data set that we used to validate our technique. This is the so-called TEX-CUP urban positioning data set. It was put together by a former student of mine, Lakshay Narula, who now works at Google's Street View team. It is 2.5 hours of driving in the urban core of Austin, Texas, across 2 different days. So this was May 9th and 12th, 2019. We did a comb, as you see on the right-hand side, in the densest portion of the urban area so that we could explore just about every street that is difficult in regard to GNSS multipath. We are taking advantage of dual antenna GNSS, a consumer grade MEMS IMU, and an industrial grade MEMS IMU as some of the primary sensors for this data set. This is the so-called Texas Sensorium. It is the sensor box on the vehicle that we were driving around. It has radar units, it's got stereo cameras, it's got various inertial sensor. But for this paper, what's important were the 2 GNSS antennas on the roof of the sensorium and the 2 inertial sensors inside the box. These are low-cost MEMS inertial sensors. In the one case, it's a consumer grade, so you're talking $1 or $2. And on the other case, it was an industrial grade inertial sensor, which in large quantities might end up being $10 or $15. This is a view of one of the streets that is part of the data set. And this is a view of another street, a more light urban area, but nonetheless challenging because of the overhanging foliage and the tight, say, European style streets. The TEX-CUP ground truth, the basis against which we compare our solutions to determine how far off we are, was developed using in a partnership with Ixblue, which is now Exail. We are grateful for their partnership, and JB Lecombre was our point person there. He was very instrumental in us getting access to the top of the line Atlan C box and the recent Asterix 4 from Septentrial. So this is a forward, backward, smoothed ground truth, and it's known to be good to within from 2 to 20 centimeters accuracy. And as I said before, only the Sensorium GNSS antennas and the MEMS inertial sensors were involved in the Yoder paper research. We weren't trying to tap into the vision or to the radar. In this case, these can be layered on later on, and in fact, some of our ongoing research is layering in those sensors. So just like I like to do, we're going to jump right to the results, and then if I have caught your interest well enough, we can go backwards and talk about what's under the hood, what makes our algorithm tick. But first, let's consider the results. In the paper, you'll find this important table, which summarizes all of the testing that was done against the TEX-CUP data set. You'll see that we have the May 9th and the May 12th day here. And importantly, in this first column, we have what's called the fixing probability. In other words, this is how often, what percent of the time, we're able to declare a fix in our tightly coupled inertial GNSS precise positioning. This is an integer fix. And what's astounding here is that with these low-cost IMUs, we are able to get very close to 100% fixing. Compared to the unaided case where we don't have an inertial sensor, where we only got 77 or 76% fixing, we're getting 94 to 97% fixes So this is availability of the precise solution. The second column here shows you the probability of false fix, and the third and fourth column talk about the precision of the fix, or the accuracy in terms of the 95% errors. Let me zoom in on this section here so that you can appreciate the numbers we're talking about. The 95% errors you see for the consumer grade IMU on May 9th were 20 centimeters. If you go to the industrial grade, it drops down to 13 centimeters. Again, on May 12th, it's 13 centimeters and drops down to 12 centimeters. And this is for a false fix of less than 0.5% or thereabouts. How do we determine false fix? That was determined against the ground truth solution. So these are what I consider to be really remarkably good results for an urban area. We haven't seen anything published that comes even near these results. You can take a look at them from a different perspective, say from the cumulative density function here on the right-hand side. The upper trace is for the consumer grade IMU. This is, like I say, $1 worth of an IMU, and the lower one is the industrial grade IMU. If you take a look at the solid line, these are the epochs where we had fixed the solution. In other words, this is like the 95% of the time where we're able to fix the solution. Whereas the dashed line, these are all of the epochs, whether it's fixed or float. And you can tell that in those cases where we fix, which is, as I say, very high probability, our CDF is excellent. We tend to have even very, instead of thick tails, we have fairly thin tails in the CDF. So during the times where we have a fix, the fix is almost always exactly correct. And this is a different view from, say, the error in the east-north up under 3 different configurations: the unaided configuration, no inertial aiding, the consumer-aided configuration, consumer-grade IMU aided configuration, and the industrial-grade IMU configuration. You'll notice in the left-hand plot in the lower panels that there are these gray intervals. The intervals that are grayed out are ones where we did not have an integer fix. And you can see, of course, that the error growth in those intervals is much larger than in those cases where we had a fix. But the error growth is curtailed by the inertial sensor and also by some vehicle constraints, zero side slip and zero velocity update constraints. In the right-hand side, you see a zoomed in view, and you can appreciate that every once in a while, we do have some excursions during times where the fix is not available, but those excursions and those excursions would exceed, say, the 30 centimeter requirements that you might have in cases of a self-driving car. But they happen very rarely, and this was just a combination of inertial plus GNSS in the urban environment. Of course, if you bring in a bit of other sensing, such as radar or vision sensing, you can beat back those errors too. So if I've interested you enough that to this point that this is high performance work, then let's take a closer look under the hood of the algorithm, and also a look at the process by which we approached this problem. Our design philosophy was always to optimize the integrated system. We wanted to optimize the GNSS receiver and the CDGNSS engine, and have the CDGNSS engine, the carrier phase differential GNSS engine, incorporate the inertial sensing in the tightest possible way and in a unified, centralized estimation architecture. We always designed our subcomponents initially for optimality under Gaussian and independent errors, but then we had to adapt because, of course, in urban conditions, Gaussianity flies out the window as you deal with extreme multipath and signal blockage. It was very important for us that we had fast iteration cycles. We couldn't just work through our data in real time. It would have taken very long to come up with new ideas, implement those ideas, and test them. Instead, we're depending here on the software-defined receiver that we've built here at the University of Texas, and that has been refined a great deal over time. And this SDR runs more than 10x real time. So we're able to scream through the data, test a new idea, and iterate quickly, which we found to be absolutely essential as we're trying to work through all of the different problems that present themselves in urban RTK or urban precise position. We also needed to have fast carrier recovery and a fast assessment of the phase lock quality. All of this was part of the design philosophy. I mentioned that we wanted to do a unified optimization of the precise positioning engine plus the receiver. So in many cases, you just buy an off-the-shelf receiver, like, for example, the Septentrion that we used for our ground truth. And this off-the-shelf receiver is something you don't have much control over. Perhaps you can make some configuration changes, parameter changes, but you don't have a lot of control over it. In our case, we have been developing this PPRX precise positioning receiver for many years since I arrived at UT, and we have full control over it. It is a software-defined receiver, and we pull in data from our own reference network. In the case presented here, we were only using a single reference antenna located at the University of Texas, so we weren't using a network solution, just a single baseline solution. And then PP engine, that is our RTK, or our precise positioning engine. And we are able to optimize the joint pipeline of the software-defined receiver and the software-defined RTK engine, because we developed both of those. And I think it's very important to have an ability to optimize everything in your pipeline, not just say the RTK engine or even downstream algorithms. This is a screenshot of our PPRX receiver. We sometimes call it GRID. This receiver is well tested by now. It's been flying on the International Space Station since 2017. It's now the basis for SpaceX's Starlink GNSS in the version 2.0 and above, and also going to be part of the Starship landing system for SpaceX. So this is a well-tested, high-performance, began as a science-grade GNSS engine, GPS engine, but has really outgrown its research roots and is licensed by many companies by now. Carrier tracking inside any kind of carrier phase-based solution has to be fast. It has to take advantage of any opportunity it can, say between buildings when a signal becomes available again, but it has to avoid frequency unlock. So we spent a lot of time and effort to ensure that our carrier tracking is as robust and aggressive, opportunistic as it possibly can be. This trace here shows you the I in green and Q in red correlation outputs for a particular GNSS signal that is being tracked as we drive down a street. You can see that as we go under a traffic light, there is some trauma to the carrier phase. As we go, as the signal is blocked behind buildings, the signal drops very precipitously to where it would be almost impossible to recover. But then there's this glorious moment where there's a glimpse of the signal again between other two, as the vehicle passes between two buildings. Those glimpses are important if you can make use of them, if you don't have to spend 5 to 10 seconds vetting your carrier phase, but can make use of it almost immediately, then you can cobble together, in many cases, enough of the signals to get a confident carrier phase differential solution. So just as a kind of recap, the different top level strategies here. We want to do tightly coupled multi-antenna carrier phase differential GNSS with a low-cost MEMS inertial sensor. We are taking advantage of vehicle dynamics constraints, the non-holonomic constraints. These are zero side slip constraints of the vehicle, and zero velocity updates. So as soon as we can tell that the vehicle has come to a stop, we can help to calibrate the inertial sensor and ensure that it drifts as little as possible, even though we're dealing with low cost, low quality inertial sensors. Also, one of James's great contributions was to put all of the estimation together in a single unscented Kalman filter. It consumes all the measurements so that the integer fixing benefits directly from the IMU constraints, from the vehicle constraints, from the multiple baselines involved. Doing this all in a single estimator was not something that our laboratory had ever been able to achieve previously. We had kind of a tiered hierarchical estimation architecture previously, but James put it all together and got better performance thereby. One of the things he worked on especially assiduously was the carrier phase false fix detection and recovery. So anyone who has had a chance to work with integer fixing in carrier phase differential GNSS understands that a false fix is highly problematic and can corrupt subsequent measurements. But if one can detect a false fix and recover from it, then one benefits from the extreme precision of carrier phase positioning. Our technique for dealing with false fix detection and recovery was based on an insight that James had to develop a two-part estimation strategy, a primary estimation pipeline and a float-only estimation pipeline. And then there are these behaviors that occur between these two such that you don't get caught in a corruption for very long if there is an integer error that creeps in. Let's consider the top panel here. Our primary estimation engine is the one that tries integer fixing. But if, as it moves along, its integer aperture test fails, then it gets a soft reset of its position from the float-only solution, which was never corrupted by any of the integer fixing that was occurring. So the soft reset brings in a less accurate but uncorrupted estimate of the vehicle's position and orientation. Now consider the second panel. This is a case where the primary integer fixing estimator has what it considers to be a very good solution. As soon as it has declared itself to be a very good solution, then it can reseed the float-only estimator by providing it a constraint on the float position. And thereafter, the float-only acts only with the float double differences. James found this technique offered a way of doing false fix detection and recovery that was superior to anything we had tried before. It should also be noted that our integer fixing technique is one that has a very short memory. We are throwing away all previous integers that have been fixed at each epoch. So we only carry forward the integer conditioned positions, excuse me, of the vehicle, but we don't carry forward the integers themselves. We have found that this technique works best in urban areas because during many intervals of time, you will be locking onto, you will be experiencing phase ambiguities basically continuously. And so we never made any attempt to try to heal those phase ambiguities or to relate current phase double difference phase measurements with previous double difference phase measurements. Instead, we just estimate them fresh every time. And as long as you have enough signals and enough of a prior constraint, you're able to do this with high reliability. One of the kinds of testing that we did, I think is fun and illuminating. We call this destructive testing. So we go through and we have a look at all of the tricks that we threw at the problem, and then we remove these one by one and ask ourselves, how much of an effect did it have on the final solution? The top row here is our baseline configuration with all our features enabled. And each of the subsequent rows is removing one of the features, one of the tricks that we threw at the problem. So for example, configuration 2 is a single vehicle antenna configuration instead of the 2 antenna configuration. And what you notice is that the degradation in performance is not terribly striking. We go from 97.5% availability of a fixed solution to about 97% availability. Our probability of false fix goes up a bit, and our probability, or our 95% error diameter goes up, or radius goes up. But it wasn't a remarkable drop-off. And so the techniques that we've developed work decently well with single antennas also. If you take away the holonomic constraints, now keep in mind that these configurations are taking away these constraints or these tricks one at a time. So it's not like this is cumulative. If you take away the non-holonomic constraints, very little change. You take away the zero velocity updates, very little change. Outlier exclusion does really affect your probability of getting a fix, your availability. and the reseeding and the false fix detection and recovery are the ones that really show the remarkable differences. So if you throw out our dual estimator track false fix detection and recovery technique, then your probability of false fix balloons up to 24%. Of course, you've got a high availability, but a lot of those are garbage. And then your actual positioning positioning error is very large. Then you can take a look at single frequency. So remarkably, the single frequency approach, we were usually using dual frequency L1 and L2 with GPS and Galileo and WASP. The single frequency approach was not much worse than the dual frequency approach. And that bodes well for even lower cost variants. And then if you take away the WASP variant, you do see some hit here, because those WASP signals, the way we use them, in SBAS signals, WASP signals, are actually quite useful. There's a bonus to all of this. The bonus is that once you have an estimator that is tracking the carrier phase of the GNSS signals and is predicting forward the vehicle movement based on an inertial sensor, which is sensitive even to, say, high frequency vibration caused by the road or undulations caused by road roughness, then you're able to detect if there's any mismatch between the carrier phase measurement and where you predicted it to be. Now, of course, some of this mismatch comes because of the multipath environment in the urban area. But a significant mismatch might indicate that you're being spoofed. So as a bonus of the tightly coupled GNSS carrier phase differential plus inertial sensing estimation engine that James created, we're able to offer anti-spoofing. And the basic idea is that this can address even the most dangerous, most nefarious, most subtle kind of spoofing you could possibly imagine. Imagine that every line of sight to every legitimate GNSS receiver was occupied by a drone that is transmitting just the signal from that, just a spoofing signal that tries to mimic the GNSS satellite in the line of sight. So it effectively overpowers just that one signal, broadcasts the fault signal, and yet all of these signals arrive at the vehicle antenna in such a way that the spatial distribution in the sky of the signal angle of arrival is consistent with the actual spacecraft locations. This is a very challenging spoofing scenario because many of the anti-spoofing antennas are looking for a discrepancy between the advertised and the measured angle of arrival. Anyway, in this case, they're still not able, in any practical sense, to predict the ups and downs the vehicle will experience as it drives over rough road surfaces. Yet the inertial sensor inside the vehicle is able to predict that and make a consistent prediction of what the next carrier phase should be. So it's extremely difficult, I would say, verging on impossible, even for a very expensive coordinated spoofing attack, to overcome the precise measurement prediction that the tightly coupled method James developed is able to offer. And you can read more about this in another paper that my student Zach Clements wrote, where he took James's estimator and found out ways to develop a detection statistic for spoofing that we have found to be highly sensitive and very difficult to fool. So an added bonus of tight coupling is that you can address one of the other failings of GNSS, namely that it has some security failings, not just susceptibility to multipath. So the takeaway message that I have is straightforward. It is that if you combine precise GNSS, even with low-cost MEMS inertial sensing, a vehicle model, and some fancy processing that is enabled by having very fast iteration cycles that themselves are enabled by a software-defined GNSS receiver, then you're able to provide a path to low-cost sub 15 centimeter, 95% GNSS based absolute positioning in urban environments. And we believe that this is a path largely unexplored in the world of self-driving vehicles. Of course, all these vehicles have GNSS receivers. And in the case of the GM Super Cruise, they're even using a variant of PPP positioning to do lane level localization. But much better than lane level localization, we believe is required long-term for to keep the risk allocation of the pose estimation subsystem down below acceptable limits. And with the technique that we've discussed today, you can, for very low cost, get down to 15 centimeters, 95%. Whether this is overkill or whether it's not good enough depends on your application and on other subsystems. But we believe that something like a target of 30 centimeters, 95%, which is what the Ford people came up with a few years back, is a reasonable benchmark. And we're meeting that and exceeding that by quite a bit. So we encourage you to read over the paper, and we welcome any of your questions and comments.
Thanks so much. This has been it's been a great presentation. Please enter your questions in using the Q&A button in your viewer, and we will address those with Professor Humphreys. Just to get us started while we're waiting for some questions to come in, let me start with this question. Of all the challenges that face autonomous vehicles, I mean, they operate in highly dynamic environments. So of all the challenges, where does PNT rank in the priorities? Is this in the top 5, top 10, top 1?
Yeah, that's a great question. I would want to emphasize somewhat modestly here that I don't think PNT falls in the top 1, 2, or 3. Of course, vehicles such as the Waymo vehicle, the cruise vehicles, are just festooned with sensors. They have LiDAR, they have radar, they have cameras. And in a relative sense, they know their location and orientation with the local map highly accurately in almost all conditions. And so they don't really depend so much on GNSS. And when things fail, they fail often for reasons of interpreting the environment, reasons of perception. Is that pedestrian going to step out onto the road, or is he not? Should I brake very hard right now against the possibility that he might step out onto the road? These kinds of issues. But just weeks ago, I read an article about the cruise testing in San Francisco, where many vehicles were brought to a halt because they were not able to see through the fog. And not being able to see through the fog, they couldn't even determine their location confidently. So I believe that in cases where you want to deal with inclement weather, your vision sensing may be compromised. And especially in cases where you have very few radar reflectors, you definitely would like to have a backup GNSS system in that case. So for open fields out in the in the hinterlands on the highways in Nebraska, you would definitely want to have precise positioning. Of course, the focus of our paper here is in the urban environment, but we believe that even in the urban environment, having a backup precise positioning or GNSS-based positioning, absolute positioning, is highly relevant. And as you saw in that video of Tesla, it just seems like it ought to be built in to every self-driving stack. Don't let use what is available, use what is cheap and is available, even if it's say historically had a poor reputation in your view.
Interesting. Okay, yeah, good answer. So we have related questions to this. One comes from Stefan Beauregard. He says, what is your view on the use of onboard automotive sensors, such as ABS wheel tick sensors on 4 wheels, the steering angle sensor, brake sensors, and so forth, for vehicle modeling?
Yeah, that's a great question. We did not use such sensors in the research behind our paper. Instead, we were using a vehicle model, zero side slip, and so non-holonomic constraint and the zero velocity update. But provided those sensors can offer fairly unbiased measurements of, say, the wheel tick movement and the steering wheel angle, a bias that doesn't change radically over time, say, then they could be of great use. One of the best things, and I should emphasize this, one of the best things about having a carrier phase differential solution on a vehicle is that you're able to do effectively laboratory quality calibration out on the roadways. You're able to calibrate, for example, those wheel tick sensors against very accurate positioning. You're able to calibrate the model for your steering wheel angle sensing out on the road with, as I say, laboratory level precision. So calibration, I think, is the unsung application for precise positioning on vehicles. And each of these other sensors, even if they come with a bias, provided that that bias doesn't change too radically over time, can be, I think, very useful to further constrain the estimates. And I really think that that would be the logical next step. So we moved from pure GNSS with just a vehicle model to pure GNSS vehicle model and now inertial sensing. The next step, of course, just use the onboard wheel tick sensors, onboard steering angle sensors. And then once you've gone that far, you can ask yourself whether you need to bring in some sort of tightly coupled variant of vision aiding or radar aiding. So I do think the wheel tick sensors and other inbuilt sensors could be really beneficial because they can be calibrated using GNSS as long as you have some intervals where the GNSS is confident.
That's fascinating stuff. And it seems like we're, as advanced as this is, we're still at the beginning of this. So that's really great. Next question comes from Professor Mark Psyche. I believe you two are well acquainted, who asks, do you use some sort of tightly coupled features in order to quickly reestablish carrier phase tracking after passing into a building shadow?
Thanks, Mark, for the good question. If we pass into the shadow of a building, we are paying close attention to the I and Q correlation products, and we have ways of detecting very quickly whether we believe we're in phase lock or not. As soon as we fall out of phase lock, we ensure that all of the downstream processing is well aware that the GNSS receiver doesn't claim to have phase lock on that signal. And none of those carrier phase measurements are subsequently used. But as I mentioned, it's very important to be able to recover and declare phase lock as soon as you possibly can. So instead of having several layers of vetting, we declare phase lock as soon as our low-level phase lock detector has indicated such. And then we depend on the downstream processing to deal with the fact that we may have slipped many, many cycles between the last time we had phase lock. As far as features go, we're not really paying attention to features. We're just building a phase lock statistics that is based on the I and Q data and a short past history of those data. We're not trying to interpret the particular variations that would come from, say, driving below a semaphore or driving behind a building. We simply let the statistical phase lock detector do its job, but we constrain the history so that it reacts quite promptly once you get a glimpse. Because what we've noticed is that phase availability is very much a binary condition in the urban environment. Either it's pretty hopeless or it's decently available. And so we want to be able to check those and find the decently available intervals and use those to full ability.
Okay, great. Thank you. This following question comes from Ramachandra, who asks, how critical was the use of the unscented Kalman filter versus a more standard extended Kalman filter as your fusion filter?
Yes, that's a good question. In the paper, you'll see that James spent a lot of time developing a technique whereby the unscented transform was used to deal with the baseline between the two antennas on the vehicle. In particular, he was looking at ways to ensure that the baseline constraint could be used as quickly and accurately as possible, even though it was a highly nonlinear constraint. And the truth is that in the end, as you can see from this chart, if he had done an EKF update instead of the UKF update, the numbers don't change a bit in the data that we collected. In other words, the unscented common filter update was not the secret to our success. However, we do believe that in cases where you are initializing your estimator from a really poor a priori solution, that unscented common filter update for incorporating the baseline constraint would become more important. It's just the case that we never got so far off we never got so confused that our prior pose solution was far enough off to show the benefits of the UKF solution. So yes, I believe this could have been done with an EKF. However, we like the UKF not just for its performance, but because of its flexibility, its adaptability. We're able to change measurements very quickly, and it's not like I'm afraid of taking a derivative. I don't mind that, but I have a large code base to maintain, and errors can creep in when you're trying to find Jacobians for complicated measurement models. And it's just lovely to throw this into a UKF and not have to worry about that.
Okay, great. We have another question from Dr. Psyche. He says he's not sure that the claims about anti-spoofing will hold up for a variety of spoofer directions. Wouldn't the natural high-frequency phase variations of spoofed signals caused by the physical change of length along the independent spoofed paths correlate well with the INS high-frequency motion? How could one even be able to make a definitive statement about such things without doing live signal spoofing tests, which he assumes you have not done for a multi-directional spoofing attack?
Right. Creating that kind of an attack, the one that we imagine, is even expensive to think about. So no, we have not run that test. We have in the paper run tests that act very similarly to this. What we've done is to demonstrate that if we take actual true live data and we fast forward it or slow it down so that what you're receiving at any given time is discrepant with what the IMU timestamps expect to receive, that we are able to detect the case and flag it as a spoofing. So basically, if your time consistency between the IMU and the valid GNSS data just gets off by even a few seconds, we're able to detect that. And that's it's actually a fairly strong indicator that the spoofing attack I described would be detected. The geometry does depend on the the spoofing detection statistic does depend on the geometry, the line of sight geometry to each one of the satellites. But think about it from the perspective of each one of the drones trying to carry out the spoofing attack. It's going to be trying to mimic the overhead signal, and also perhaps trying to track the vehicle in such a way that it could anticipate what kind of carrier phase variations would occur. But those carrier phase variations are not going to be common mode. Imagine a vehicle that's just vibrating up and down, up and down. Well, then the drone directly overhead will need to compensate quite a bit, whereas the drone at a larger slant angle will compensate much less. And so the statistic shows a sort of tearing apart of all of these the spoofer's inability to track the actual carrier phase. And in fact, it's very hard for the spoofer to come up with a way to anticipate the ups and downs and side to sides, a high frequency up and down and side to side of the vehicle. So I do think that the paper that Zach wrote gives a hint about how this will be useful, but we are planning a second test whereby we hook the antenna on a moving arm and we'll hope to show the empirical results in that case, not just fast forward and slow down the time stamping.
Okay, great answer. Thank you. Our next question is from Thomas Paney. Welcome, Thomas, who says, would you expect a significant benefit by moving from tight coupling to deep coupling, for example, vector PLL?
Good question, Thomas. Thanks for joining. Yes, so what we're doing here is tight coupling. The software-defined receiver we have was not directing its tracking loops based on the inertial sensing. However, inside our software-defined receiver, we are doing vector tracking. It's just with a really, say, unsophisticated vehicle model. We weren't driving it with a model driven by the inertial sensing. But that vehicle model is basically a nearly constant velocity model, is actually quite powerful in offering some robustness to the vector tracking solution inside the GNSS receiver. I do think that there could be quite a bit of benefit to fully closing this loop and offering inertial sensing to the tracking, but that is one step that will probably be very hard for us to build into our current software-defined receiver, just because of all of the requirement to determine your attitude before you can start applying those the inertial sensing. We are hesitant to take that approach just because we know that there will be many bugs that will pop up that will be harder to evaluate, because now we will have a fully closed loop system, and the bugs that come from the inertial sensing and from the integer fixing are now going to affect our tracking. So we may take that approach in the future, but we're getting a lot of bang for our buck, even with it not being deeply coupled.
Okay, thank you. We do have a question here from Michael Eglinton, who says, can you comment on initialization? In the paper, you mentioned that prior knowledge of attitude is helpful. In real operations, vehicles are often moved while the positioning system doesn't have lock. How quickly and easily can you initialize from a cold start? Yeah, that's a great question, Mike. Part of the main reason that James explored this unscented transform for bringing in the baseline constraint of the vehicle was so that we could lock into a pose estimate very quickly, even starting from a highly erroneous attitude estimate. As regards the integer fixing, it's really remarkable nowadays how fast you can resolve all of the integers in an integer solution, even if you have partial visibility. So keep in mind that, as I said in the presentation, we're doing single step integer fixing, which means we throw out all of the previous integers at every epoch. And when you're starting with errors at the meter level, even at the 1.5 meters, maybe 2 meter level, that integer fixing happens instantaneously. Now, every once in a while, you will make a mistake in the integer fix. And so it does become a challenge to determine, say, in a cold start scenario, starting between buildings, whether you have locked on to a false integer. That becomes obvious only as you begin to move and you accumulate discrepancy that the false fix detection and recovery algorithm I mentioned finally finds, and then starts the recovery technique. But it is, I would just say, it is remarkable how quickly you can get to an integer fix. We're not talking PPP here. This isn't a 10-minute, this isn't a 5-minute, this isn't a 1 minute. This is an instantaneous fix. And you can use that to your advantage as you come in and out of signal availability. Great, thank you. Our next question is from James Hugh, who says, how do you detect equipment failures and defects, for example, in antennas? Right.
At present, we are detecting failures only, say, of the inertial sensor or failures caused by spoofing. But failures caused by the antennas themselves is not something that we've built into the robust pipeline of the estimator. So if our antenna were to fail, one of the antennas were to fail, the most probable outcome would be that we would start to experience integer fix failure. And as you saw, we're able to deal with integer fix failure. Say, if you go from 2 antennas down to a single antenna, we can still keep going in that case with almost the same performance. But the, say, baseline fix would not be available. And so there is some robustness built into this, but we haven't, it isn't modeling particular failure modes. It is simply the case that you can excise certain features and things continue to work, but we haven't got an exhaustive list of particular failure modes. That would, and such a list would be perfectly reasonable as you move toward production, toward actually implementing this in production.
Okay, great, thank you. A question here from Christoph, who says, how much of the false fix and recovery process depends on the environment? For example, urban canyon with degraded GDOP and signals.
Well, you hardly ever engage in this false fix and recovery process unless you're in an urban environment. Out in even a light urban environment, we almost never have to tap into the, say, reseeding from the float only solution, or the other way around. So yes, only in the deep urban environments do we tap into this technique. And it becomes fairly common when you're driving down an urban canyon, tall buildings on both sides, you're recovering and reseeding, say, every 10 seconds, 15 seconds or so. It does depend on the severity of the environment, but it's not actually as common as I might have given the impression. We're not talking it happening every epoch. You go a long ways before you ever need to draw from the float only solution.
Okay, thank you. Our next question is from Henry Martin. He says, your result on SBAS removal implies that SBAS is perhaps a geometry benefit. Can you elaborate on why this is a relatively large effect? Are you doing something? Let's see. I think that part got cut off. So that is the question from him.
Great question. There are 2 reasons why SBAS is so useful for us. First of all, there are 3 SBAS satellites visible to us here in Austin, Texas, and we were using all 3 of them. They are fairly high elevation. We're talking 35 to 45 degrees elevation, and that's useful. Anything above, say, 20 degrees elevation is a signal that we are willing to contemplate using. But if you're even as high as 45, that's quite nice. Now, the other thing that you'll learn about by reading the paper and by reading the predecessor paper is that we're doing some fancy processing with SBAS, just as we are doing it with L1CA. We are wiping off all of the data modulation on SBAS and wiping off all of the data modulation on L1CA. We do this wipe off in part by looking at the patterns of the data. That works for L1CA. For SBAS, there isn't enough of a pattern historically that allows you to predict future data bits from past data bits. And so we are sending data from the reference station to the rover vehicle in a just-in-time sense, so that we can wipe off the data modulation on SBAS. This means that we're getting full carrier recovery, not half-cycle recovery. We're getting full carrier recovery from SBAS, just as we are from GPS L1, and it makes those signals just as valuable as GNSS or GPS signals at L1. So I love SBAS, provided you can wipe off those the high rate navigation data on the SBAS signal.
Okay, thank you. I think we have time for one more question. Let me scroll up here. This question also from Ramachandra says, what is a comparable level of performance by combining COTS GPS receivers and MEMS IMU while applying your fusion algorithm?
So an off-the-shelf GPS receiver and a MEMS IMU, you can get a sense for this partly by having a look at how well the Asterix receiver, the Septentrio Asterix receiver, which is, I believe, a top of the line, very good, say, off-the-shelf receiver that works decently well in urban areas. Have a look at how well it does just on its own with no inertial aiding. And then ask yourself how it would do with a low-cost inertial aiding. Keep in mind that it was this Septentrio Asterix receiver plus a $65,000 or so high quality X-Blue Atlan C inertial sensor that offered the combined forward-backward smoothed truth solution. But if you take away the X-Blue inertial sensor and you're only dealing with the Asterix receiver as it was, its performance is the fix availability, for example, hovers around 60%. Okay, so it's actually even worse than the fix availability of the current technique of our technique in cases, let's see, up here, I can show you, of our technique in cases where we were not being aided. So the unaided is 77% here and 76%, whereas the Asterix was, for the same probability of false fix, was hovering around 60%. So if you were to combine that with an inertial sensor, I don't believe that it would bring it up nearly to the availability that we were getting, but I did not do that combination. As I said, our design philosophy, we want full control of the whole pipeline. We don't want to have to worry about what might be going on inside an off-the-shelf receiver. And that's part of the secret to our success, is that we have full control of the pipeline.
Okay, well, thank you again for this great presentation, for taking the time to answer questions. I'm sure we could sit here for many hours and continue on. It's obviously a topic of great interest to our community, and the research you're doing is very valuable. So we appreciate your time to present to us today.
And I appreciate everybody who took his or her lunch break to come and listen to the presentation. And shout out again to James, who is probably looking at Starship launch contingencies right now, and hope that he gets full credit for this paper.
Absolutely, and we wish him well in his current work there. And as a reminder to our audience, this webinar has been recorded and will be available on our website and social media channels later this week. And you can, in the meantime, download the full technical paper from our website at NAVI, that's navi.ion.org. Thanks, Professor Humphreys, and to our audience, have a great day wherever you are.